Hi, I'm Antoine, and I will present our paper Macaron, Mapping and Coverage Anticipation with RGB ONline Self-supervision. In this work, we focus on the next best view problem for automated 3D reconstruction using an RGB camera. For an autonomous robot exploring an unknown 3D scene, the goal is to identify where to move the camera next to improve the coverage of the scene. Indeed, when using 3D reconstruction methods such as a structure from motion or neural radiance fields, input images should not be captured from random locations. The more they cover the whole surface of the scene, the better the reconstruction should be. In this paper, we build on our previous work SCONE, which is a supervised NBV method using a depth sensor, and we introduce another approach called Macaron that allows for learning simultaneously to explore and reconstruct in 3D new large environments from color images in a self-supervised fashion. Self-supervision actually allows for training the model in any large environment without an oracle, which results in even better performance for large 3D scenes than our previous supervised approach. Now let's take a closer look at what the NBV problem is and quickly discuss the limitations of previous approaches in literature. NBV is a long-standing problem in robotics. Based on partial knowledge of a scene at time t, it consists in determining the optimal camera pose at time t plus delta t to maximize the coverage of the scene. Depth sensors are commonly used, but sometimes RGB images are used as inputs instead. The general idea behind next best view algorithms is, for any camera pose in a scene that could be a candidate for NBV, to provide a score describing its quality as the next view. NBV is finally selected as the camera pose with the highest score among a set of candidates. The lack of scalability is the main limitation of previous approaches that either rely on memory-heavy representations and costly operations, suffer from heavy restrictions on the size of the scene, or constrain camera motion to a predefined set of camera poses. Our previous work introduced a scalable approach called SCONE, which learns to predict how much any new camera pose increases the coverage of the scene. This approach scales to any large 3D scene at inference. Moreover, it uses a 3D representations with virtually infinite resolution and handles completely free camera motion. However, it needs explicit 3D supervision with a heavy oracle. Therefore, it is impossible to train SCONE in large 3D scenes where such an oracle is too difficult to compute. Additionally, the use of a depth sensor further complicates its application in real-world scenarios. In this paper, we introduce a method called Macaron that trains SCONE in a fully self-supervised way from RGB images and show that it results in better performance for large 3D scenes. Indeed, self-supervision from color images allows for jointly learning, exploration, and reconstruction without an oracle. As a consequence, it is possible to train the model in any large environment, which explains the gain in performance. As I explained, the next best view is commonly selected as the camera pose that maximizes the gain in surface coverage. First and foremost, let's begin by defining what surface coverage is using a simple illustration. Let's say a drone is exploring a 3D scene like the Alhambra Palace, following this trajectory. The sensor has captured depth maps that can be back projected into 3D surface point clouds. Here, the current surface coverage is the area of the surface covered by the depth maps divided by the area of the total surface of the scene to explore. Now, let's see how Macaron uses RGB images as inputs to explore a scene while maximizing the surface coverage. First of all, let's recap all the inputs we have at time t. The RGB images, the corresponding camera poses, as well as a 3D bounding box that delimits the spatial extent of the scene to explore. Our goal is to jointly learn how to explore and reconstruct a 3D scene. In practice, at each time step t, we want our model to perform two different tasks. First, for any candidate camera pose that has not been visited yet, it should be able to estimate how much it will increase coverage. Then, it should reconstruct and update surfaces from last capture color images. To achieve these goals, we use three different neural modules. The first neural module is the depth module. From the last capture frames, the depth module predicts the depth map for the current frame at time t, which is added to the previous depth maps. We call the second neural module the volume occupancy module. From the surface visible in all previous depth maps, in purple, this module computes for any 3D point in the volume the probability the point has to be occupied given the past views. The brighter the point, the higher the probability. The third neural module is the surface coverage gain module. Using the previously predicted occupancy field, for any camera pose that has not been visited yet, this module predicts how much this camera pose will increase surface coverage. In particular, we sample points in the field of view of the camera according to their predicted occupancy probabilities. Then, The module predicts gains in visibility of all samples in the direction of the camera pose. These visibility gains are aggregated in order to estimate the surface coverage gain of the camera pose. The true innovation of Macaron lies in its training process that allows for online and self-supervised learning. The main strategy to self-supervise the model consists in computing pseudo-ground truths at time t during exploration and use them to supervise predictions made with data collected prior to time t. We employ a warping strategy to self-supervise the depth module, similar to many other methods in the literature. Therefore, let's focus on generating a self-supervision signal for the remaining two modules. For the volume occupancy module, we build a pseudo-ground truth occupancy field using our predicted depth maps. In particular, we rely on space scaling operations. The key idea is the following. We suppose that all points located behind the depth map are occupied, while those in front are empty. As the trajectory progresses, we update this pseudo-ground truth occupancy field by considering a point occupied only if it is located behind all the previous depth maps. For a surface coverage gain module, at a given time t, we use the depth module to predict the surface points already visible in the image captured by the camera. As the trajectory progresses, we predict new surface points visible by the camera at time t plus delta t and distant from the points that were already visible. We finally use the number of newly visible points as a supervision value for the surface coverage gain of the new camera pose. To perform a full training iteration using our pseudo-ground truths, we follow a specific memory replay pipeline with 3 steps. First, at each time step t, we apply our 3 neural modules to select the next camera pose to visit at time t plus delta t. We call this step decision making. Then, we move the sensor toward the next pose and gather data along the way. In particular, we capture RGB images and predict corresponding depth maps. Next, we use these depth maps to update the pseudo-ground truth occupancy field and compute the pseudo-ground truth surface coverage gain for the new camera pose. Then, we store this data in a buffer called the memory. Finally, we load self-supervision data from the memory and perform a few training iterations. Memory replay avoids catastrophic forgetting and significantly speeds up training compared to a training procedure that uses only recent data, as such data is highly correlated. Even if it only uses RGB images, Macaron is able to outperform baselines in NBV computation for dense reconstruction in large environments. Indeed, contrary to other methods, its self-supervised online training strategy allows it to scale its learning process to any kind of unknown environment, where no ground truth or oracle are available and data has to be acquired with a camera.